just physics. Now, I was able to perform that amazing trick shot, not just because I'm amazing at basketball, but because I'm amazing at physics. The trick, you see, is to split the velocity of this ball, or projectile, into its two component parts, vertical and horizontal. Now, in order to do that, let's first of all visit vertical world. In this world, we're only ever considering the vertical velocity of this ball. Now, vertically, this ball is being pulled towards the ground by the force of gravity all the time. That means that when it's rising up, it's slowing down because it's getting pulled downwards. And then when it falls gracefully and majestically into the basket, it's speeding up because it's getting pulled down. Now, for nat 5, you only ever have to consider the fact that it's falling down. Okay? You only ever deal with projectiles which are falling towards the ground. So for your point of view, the vertical velocity of this ball always increases downwards. But this whole gravity business is getting me quite down. So let's enter horizontal world. In this world, we're only considering the horizontal velocity of this ball. Horizontally, the velocity of the ball never changes. It is the same the moment it leaves my hand, to the maximum height, and then back into the basket. Okay? It never changes. If you pushed a Rangers fan off a cliff, the horizontal velocity they had when you pushed them off would be the same as the horizontal velocity they would have when they were smashed into the water at the bottom of the cliff. Horizontal velocity never changes. Let's wrap those things up together in a handy simulation. So here we have a cannonball being fired out of a cannon. Okay? And we're first of all just going to look at the horizontal component of the velocity. If we look 5 seconds into the future, 1, 2, 3, 4, 5, you can see the ball has travelled that distance. If I play another 5 seconds, 1, 2, 3, 4, 5, it has travelled the same distance. It's travelled the same distance because its horizontal velocity hasn't changed. We could play another 5 seconds, 1, 2, 3, 4, 5, and again it would travel the same distance because the horizontal velocity never changes. Let's now take that back, but this time we're going to consider what it's doing vertically. So once again, let's play 5 seconds. 1, 2, 3, 4, 5, and it's not travelled very far at all. 1, 2, 3, 4, 5. In the next 5 seconds, you can see it's travelled a little bit further. And it's travelled further because it's speeding up. Its vertical velocity is increasing all the time because of the pull of the Earth's gravity. 1, 2, 3, 4, 5 seconds later, and once again that gap, that distance travel is even bigger because its vertical velocity has increased even more. Okay? Now, in reality, the horizontal component of the velocity does decrease slightly because of air resistance acting against it, but for nat 5, you don't need to worry about that. You can ignore air resistance. Yay for you.
Yes!
This leads to quite an interesting conclusion though. If the horizontal and the vertical components of the velocity are totally separate, right? That means that it doesn't matter how fast you throw something horizontally, it will fall to the ground at the same rate as if you had just dropped it. That means that if I fire this crossbow bolt out of this crossbow horizontally, like this, then the amount of time it takes for that to hit the ground is the same amount of time as it would take this to hit the ground, as long as they were at the same height to begin with. Okay? Which kind of makes sense, because why should you not feel the pull of the Earth's gravity just because you're moving horizontally, right? You don't become any lighter just by running. Now, if you don't believe me, and even if you don't believe this simulation, which shows the two falling at the same rate, perhaps you'll believe this story. Gather round. This is a story of a monkey and a hunter. Once upon a time, there was a monkey and a hunter. The monkey was sitting happily up a tree when he was spotted by the hunter. The hunter then proceeded to climb a nearby tree to get to the same height as the monkey and get a better view. However, just before he fired, the monkey spotted him. And very quickly the monkey decided that he would let go of the branch the moment the gun was fired, concluding that in this situation the bullet would then sail harmlessly over his head. This is what happened. As you can see, the monkey fell at the same rate as the bullet and was shot and died. The end. I hope you take that story to heart, and indeed that you understand projectile motion. You just never know when you'll be at the top of a tree being shot at by a hunter. Think about it.